Monday on mass spec and IR. And so for the remainder of this module 2, we're going to talk about nuclear magnetic resonance spectroscopy. And so this is IR stands for infrared, and that's in the region of the electromagnetic spectrum. NMR uses radio waves, but there's also another component to it, and that's a strong magnetic field. So there's a magnetic field, and then the radio waves hit the sample, and then they affect the nuclear spin. I'm not going to talk too much about the theory of NMR. It's a lot of physics, a lot of math. We're just going to qualitatively look at the spectrum and then utilize this uniqueness that we've been talking about for the semester so far. So in today's lecture, we're going to look at an infrared spectrum and still see that there is a little bit of ambiguity in it. And then from that, we're going to make two claims of what structures could be, go through the uniqueness, and then look at carbon data. If there's enough time, we'll talk about protons again. Any questions before we begin? So we saw this IR spectrum, I think Monday and Wednesday. There's still a little bit of ambiguity in it, and that's going to lead us to propose two structures. We could probably propose more, but we're just going to focus on two. And the point of the exercise is to sort of drill down into the data and see how it can support one claim or refute another. And again, the whole point of this module is, now that we know functional groups, how can we use spectroscopy to determine if they're in a molecule? Because overall in this class, as we start learning reactions, a starting material or a substrate can give more than one product. So you have this mixture. And then how do you determine what is a major or minor component of the mixture? So let's start off here. It says a compound with apparent ion of mass to charge of 72, so that's even. So no odd number of nitrogens. As determined by mass spec in the IR spectrum is shown, what are some possible structures? So we don't really see anything indicative of an OH or an NH bond in this region here. So that will eliminate some functional groups for us. This is your standard CsP3H stretching. Region 2, we don't see any triple bond stretching. However, in region 3 at 1730, there's this, what we now know is a signature for a carbonyl, so a CO double bond. And so that's helping us formulate a molecular formula. We know we have C, we know we have H, and now we know there's an oxygen. So C, H, O, and then we'll use, again, this 72 to figure out what, say, X, Y, and Z are for that molecular formula. The other thing to pull out of this information is that the carbonyl is 1 degree of unsaturation. So this question says, what functional groups could be present? So alcohol is OH, amine can be NH2, NH, or N, but we eliminated both of these based on region 1, and the fact that it's an even mass also eliminates an amine. So an ester can be that. A ketone can be that. They both have carbonyl, so that's a possibility. Alkyne or nitrile we eliminated because there's nothing in region 2, so no triple bonds. And so we have D, which is aldehyde or ketone, and we see ketone is the same in both B and D. So we need to look at the IR to sort of eliminate ester or aldehyde. So an aldehyde has the carbonyl with that H. So CsP2H. And from our last discussion, that has a unique signature that falls below the normal CsP3H stretch. So that aldehyde stretch would come over here. But the fact that it's not there means we can eliminate D. So really, within the mass spec data of 72 and the IR, we've narrowed down that the molecule could be an ester or a ketone. And so we're going to work through some proposals. We'll do the uniqueness of carbon, the unique sets of hydrogens, the ratios, and we'll look at data, and we'll see how the carbon NMR spectra looks overall, and then how it would look for an ester proposal or a ketone proposal. So let's walk through both of these. We'll start with the ester, and then we'll look at the ketone. So we have M to Z equal to 72. And say we want to consider that the molecule is going to be an ester. What then would be the maximum number of carbon atoms present in the molecular formula? So we go about this by saying, okay, an ester has, the little ball is part of the molecule we're trying to figure out. The ester has a carbonyl, it has another oxygen, and then the other ball is a carbon. So from that, what we're pulling out is that there's two oxygens. Oxygen has an atomic mass of 16, so times 2, that equals 32. And so we're going to say 72 minus 32 gives us, what, 40? And that must be the remaining carbon and the hydrogens. So we know that carbon is 12. And if we take 40 divided by 12, what do we get? So 3. So 12 times 4 is 48, and that's past 40. So it can't be that, because then we would have like negative hydrogens. If we did 2, that would be 24. That would give us 16 hydrogens. So again, if you use the CN, 2n plus 2, that's way past the maximum number of hydrogens you could have for 2 carbons. So what do we get? If we say C3, and that's 36. So 40 minus 36, that would give us 4 hydrogens. And then we said the ester has to have 2 oxygens. So that's going to be our molecular formula for the ester. So this is just asking you what it was. So C3H4O2 is choice D. We already know that the carbonyl is 1 degree of unsaturation. But since we now know the molecular formula, we'll just do the normal activity here. So CN H2N plus 2, we said N equals 3. So for 3 carbons, the max number of hydrogens should be 8. So we'll say that's the theoretical or theory. We have C3H4O2. The oxygens don't do anything to the hydrogen count. So that becomes C3H4. So C3H8 minus C3H4 gives us H4 divided by H2, so that's 2 degrees of unsaturation. So C is the response. And so using those constraints, then we can propose a structure for an ester. And furthermore, we know that 1 degree of unsaturation belongs to the carbonyl. So now we'll do the same exercise, but we're constraining ourselves to the oxygen being in a ketone. So the same deal here. There's 1 oxygen. And so oxygen contributes 16 of the 72. So what do we get for this? $56. Is my math off? So if we take 56, divide that by 12, we're going to get 4, right? So 4 is the closest one. If you do 12 times 5, that gets you 60. So again, that's past what we have to deal with. So 56 is equal to C plus H count. Number of carbons, (56) divided by 12, that's 4. And so we would get C4 H8O. And so we already know again that 1 degree of unsaturation is due to the carbonyl, but are there more than that? So that's, I think, the next slide. So C4H8O, that was the molecular formula. So now we have N equals 4. So that's C4H10. C4H8O becomes C4H8. So that leaves us with H2 divided by H2. That gets 1 degree of unsaturation, which we already know is the carbonyl. So that's the carbonyl in a ketone. So here are some proposals for the ester and the ketone using the molecular formulas we just figured out. So take a couple seconds, look at them, and see which one best matches all of the constraints we're given. What do you think? So B is in boy. What's wrong with choice A? So this is an aldehyde. And again, we eliminated that from the IR. What about C? What's wrong with C? So the ester only has 1 degree of unsaturation, and we said that it needs 2. And then what's wrong with D? This one has 5 carbons. What about the ester choice? It's not an ester. So again, this is a ketone, and then this part down here is an ether. For it to be an ester, the oxygen has to be directly bonded to the carbonyl. So we have, these are our 2 claims now of what this data could be. So now we'll go through the uniqueness, and then we'll look at carbon data for each of them. Any questions before we get started on that? So to recap how we got here, not just in Module 2, but throughout the semester so far, you've learned how different elements bond together. They form functional groups. Mass spec tells us the mass of the parent ion, which is equal to the intact molecular formula, whatever that may be. There's always C and H, and then X, Y, and Z are the heteroatoms. Oxygen's hard to tell from mass spec, so that's why we started learning IR spectroscopy. But now there's ambiguity about what that carbonyl group could belong to. And so to get the exact connectivity of carbon to carbon, carbon to hydrogen, we're going to use NMR spectroscopy. And really what that is the uniqueness. So if you understand how to assign that uniqueness set, now all we're going to do is look at the data. So the number of signals matches that uniqueness. That's the point of that exercise. The spectra will look a little different, and we'll explain why those differences arise. But again, I'm not a mathematician. I'm not a physicist. This is very qualitative. So I'll give you the cheapest description of this stuff that I can. So how can we increase our confidence of what the structure is with the parent ion of 72 and the carbonyl stretch at 1730? We came up with the two molecular formulas, but now we need to differentiate them using the uniqueness. So there's the two claims. And so again, the first number is the unique number of carbons. The second number is the unique sets of hydrogen. And then in the parentheses is the ratio. So what do you think is the best response for this? I think I heard some C's. C looks to be the correct answer. Formulating in my brain how I want to set the stage for what we do next. So, you visually determine them. Again, that's sort of, you're walking along the carbon backbone. You're seeing, when I stand here, do things look different on these pathways? So for the ester, we have three unique carbons. Now what we can start to think about is, what does the number 3 mean in terms of what we know? So you know that carbon can have different bonding patterns. So sigma bonds, pi bonds, and those can be in different functional groups, right? And so from that number 3, we can further differentiate those carbons according to hybridization. So we'll do that. We'll also do it in relation to the attached hydrogens. So all of those exercises are going to help you interpret NMR spectra. So we have 3, and if we start at the carbonyl as sort of our starting point, that's 1. What hybridization is that carbon? SP what now? SP2. Then moving over here, that's SP3, and then the final one is SP3. So you have 1 that's SP2 and 2 that are SP3. So just from that number, you've now further differentiated them. And when you see the actual spectrum, hopefully you can sort of make some rough assignments then. So notice the unique hydrogen sets is now 2 because that carbon is not bearing any hydrogens. Because this is 2, we have to report 2 digits in the parentheses, and those are the attached hydrogens. So 2 and 2. And then keep in mind that, when you add that together, it's 4. That's the total number of hydrogens. Same thing for the ketone. 4 carbons. 1 of them is sp2, and then the other 3 are sp3. Same thing. You drop down a number because the carbonyl has no attached hydrogens. Then you get 3, 3, and 2 is the ratio. And when we start learning about actual proton NMR or 1H NMR, instead of ratio, we use the word integration. And that just arises from how the software calculates the area under the curve that you see. So we just did this exercise of the uniqueness set, and now we're going to delve a little bit further into hybridization and attached hydrogens. So we'll just fill this table out on this slide, but the subsequent questions subsequent slides break it down into individual questions. In the table, we'll look at hybridization for the ester, then the ketone. All we're going to do is put those numbers in there. So for sp3 hybridized carbon in the ester, we said there were 2. So 1 and 2. For sp2, we said it was the carbonyl, so that's 1. That gets us our total carbon count, so sp, there's 0. If you're visual, you can, sort of dot these things to help you out. For the ketone, there were 3 sp3, 1 sp2, and 0 sp. So the blues are the sp3, and then the green is, sp3, and then the green is the sp2. So what you'll see is there's going to be a dramatic sort of shift in where those different hybridizations occur in the spectrum. So when you're looking at a carbon NMR spectrum, all you're sort of counting. In this region there's sp3, this region sp, and then in this region sp2. Now for attached hydrogens, the ester has no CH3 groups. It has 2 CH2 groups, 0 CH, and then it has that carbon with no hydrogens. Same analysis for the ketone. There's now 2 CH3 groups. So at carbons 1 and 4, the terminal carbons of the chain, 1 CH2, no CH, and then the carbonyl carbon, no attached hydrogens. So to recap, for the ester, the CH2 groups, we counted there's 2 of them. They are different based on the stuff that they're attached to. So this one is attached to a carbonyl plus a CH2. This one's attached to oxygen plus a CH2, so that makes them different. These methyl groups in the ketone, again, they're different. Just based on their relationship to that carbonyl, you can tell they're different. So maybe I'm just going to skip through these. We sort of answered them on the prior slide. And then there's the table that's filled in. So again, this class it's very cumulative. Everything that we're learning is going to build upon itself. So you always have to put this stuff into practice. Question? No question then?
No.
Okay.
I misread that. I thought it said only one of the CH3 for the ketone.
Yeah, I could probably make those lines a little bit darker to differentiate them. So here is simulated carbon NMR spectra. I realize the numbers up here might be hard to see on the screen, but if you have it on your tablet, you can probably zoom in. So notice what I wrote there, carbon 13. I didn't write carbon 12. So NMR, whatever nuclei it's detecting, this number right here has to be odd. I'm not going to get too much into why that is, but the experiment is detecting the carbon 13 nucleus. And we sort of already saw that with mass spec when we said that carbon 12 is like 98.9% abundant, and the isotope carbon 13 is 1.1% abundant. So the carbon NMR is detecting that C13 isotope. On the x-axis, it's called chemical shift. And that will usually see the small Greek d delta, and the unit is parts per million. The interesting thing is on the right-hand side is your zero, so 0 parts per million. And then as you go left, it increases to 200. There's not really a unit for the y-axis. You might want to think of it sort of as intensity. But it does not have a formal unit associated with it. So when you're looking at the structure of the ester, how many signals do you see? So a signal is something that's coming off the baseline. So there's 1, 2, 3. And so we said that based on the uniqueness already, there should be 3 unique carbons, right? So that's what you're seeing. And can you do one assignment of a signal to a carbon at this point? So basically what we want to do is, of these 3 signals, we want to assign them exactly to the carbons they belong to in the structure. Does anything stand out to you? Shorter, yeah, wouldn't be my first sort of most confident response. So remember we said there were 2 sp3, 1 sp2, and no sp. Does that sort of lead you closer to the water? So the one at, what's that, 168, so that's sp2. And then the two on the right at 58 and 39 are sp3. Does that make sense? If they're both sp3, they should be closer to each other, right? Then you have one that's very different. There's no attached hydrogens. So it's off somewhere else in the region of the chemical shifts. What about for the ketone? So you have 3 sp3, 1 sp2. And from the ester, if we said the sp2 carbon is further away, the same logic holds true. This one at 207, that's going to belong to the carbonyl carbon. And then these three remaining, 36, 28, and 7, are the sp3. So right off the bat, just by looking at this, maybe I'll draw a line or maybe a region. So we'll say like, so anything above 100, maybe I'll write it here. So sp2 hybridized carbons typically are greater than 100 parts per million. sp3, we'll say, are less than 80 parts per million. And then what do you think falls in the shaded region there? The sp carbons. And now what I further want to point out is, think about the functional groups that you've learned, the hybridization of the carbon atoms in those functional groups. So if you didn't have any structure shown up there, and you're interpreting this and you say, oh, okay, I see this signal here at 170 or whatever, you know that, number one, it's got to be sp2 hybridized. And then as we dig a little bit deeper into this, you can further say it's part of a carbonyl group. The other sp2 hybridized carbons that we learned were in carbon-carbon double bonds, right? And there's a further differentiation after you get past 100, whether it's in an alkene or a carbonyl. And so it's pretty apparent where that line is as well. And so we can confidently say that blue carbon is that in both cases. But then for each, we have these multiple sp3 hybridized carbons that we still want to assign the exact chemical shift to the exact carbon. And so what is the logic for doing that? Just to point out, in both of these cases, see the separation between them? So from 58 to 39, we'll say about a difference of 20 parts per million for the ester. That we call that resolution. You can see they're two separate signals. Sometimes signals can be like coincident, and that's a little harder to figure out. But we actually see resolution. What we determine from uniqueness, we actually see it in this data. Any questions before we dig a little bit deeper? So on this slide, again, today we're going to focus primarily on carbon NMR, which is the functional groups in red below. Proton NMRs are shown in blue there. Just something to point out. Again, both x-axes use chemical shift with the unit of parts per million, but notice the spectral width is much larger for carbon. It runs from 0 to about 220 parts per million. The proton data, so this is 1,3C, the top one's 1H, again 1 is odd, runs from 0 to 12. Carbon NMR data is much easier to interpret. Proton NMR data, again, will start most likely next week. It has a lot more issues with it that make it a little bit more challenging to interpret. But what this slide is showing you is starting from 0 parts per million on the right, you have your normal saturated sp3 hybridized carbon. If you attach a heteroatom to it, NOF or any other halogen, you're moving it away from 0. So the chemical shift is increasing. Alcohols in particular fall a little bit higher. Now we get into the sp hybridized region for alkynes and nitriles. We move further above 100. I'm using this word vinylic, but these are alkenes, so sp2 hybridized carbon and alkenes. Aromatic, there's some overlap with the alkenes because they're part of this double bond looking system. And then once you get above 150, that's all your carbonyl containing sp2 hybridized carbons. So if we were to overlay a carbon NMR over that, you could sort of start making these claims of, okay, it's this type of carbon in this functional group. If you don't see a signal in that region, you can eliminate that as a claim. The proton data, in this case, the hydrogens are highlighted in blue. They really track sort of the carbons they're attached to. And we'll talk more about those when we get into the functional groups for proton. So my very cheap explanation of why those signals arise. If you think of an atom, a carbon-13 atom, as a top, like that toy, you spin it. Anyone have one of those as a kid? So you spin it, right, and it has a rotation. If you watch long enough, that axis it's spinning on, it starts to have like a little wobble in it. And so that's called precession. And so what happens is you're putting your sample in a big magnetic field, and all of these spins are aligned different ways. Once it gets into the magnetic field, they're either going to align with it or against it. And so those are different energies. And then you shoot radio waves into it, and it just starts flipping those spins from like north to south or up to down. And as the spin flips back the other way, it emits the signal that's observed, that line you see in the spectrum. It's definitely a lot more complicated than that, but that's my cheap explanation of what's happening. Again, we don't need to know, you don't need to know how your car combustion engine works to drive it. You just use it, right? So we're going to get the data and interpret it. And the way that I want to teach you this is starting with methane, so CH4. So that's the simplest hydrocarbon, right? CH4. And it has a negative chemical shift, so that's possible. You're now to the right of zero. And we're going to use that as sort of our starting point. And if we think of every carbon in a molecule as methane, where you're taking H's and substituting them for other stuff, you're moving it more past zero. And depending on what you're substituting it with, it's then going to lie in one of those different regions we saw on the prior slide. So we're taking CH3, H, and then for every H, we're going to substitute it for something, and it's going to move that signal into a different chemical shift. So I'll walk through maybe entries 1 and 2 on this table just to show you the logic. I'm just going to say methane, the carbon. Now we're only talking about the carbon. The carbon occurs at about zero. If we take one of those H's and then substitute that for a CH3 group, we've now made ethane. So I'll call this 10. So here's about 5. We're going to take an H, substitute it for a CH3 group. So the effect of adding that extra carbon, this should be 5. That puts ethane at, the carbons in ethane at about 6.5. If you take 6.5 minus negative 2.3, that's where this number plus 8.8. So if you're picking up what I'm putting down, where would you expect that central carbon in propane to occur? Huh? Well, you can think of it this way. You're going to take ethane, you're going to take one of those H's and add a CH3. So you're essentially doubling that. So maybe like 15, 16. So it's an additive chemical shift for every H that you substitute. Carbons 1 and 3 in propane should still occur about 6 to 7 parts per million. if you look at this next series, entries 3, 4, and 5, you're now putting heteroatoms in. What's the chemical shift trend here doing? So it's increasing, so further away from 0. And why do you think that is? Electronegativity. So if that would be my response for pretty much anything. Remember that electronegativity increases towards fluorine. So as you substitute H for a heteroatom, you're pushing that chemical shift further away from 0. And again, this last column is just showing you the difference between the chemical shift that you see, so minus and then minus 2.3 is going to equal the number that you see in that third column. So notice now the halogen series, they act a little bit weird. That chemical shift trend starts going back towards 0. And the way to think about that is when you move down this, so this was electronegativity, but when you move down that group, what happens to the size of those halogen atoms? They get bigger and bigger. And so there's less orbital overlap between the carbon and the halogen. And essentially what that does is affect how the radio waves interact with the carbon in that experiment. And we already saw from mass spec, those have signatures in them, so you can use that as corroborating evidence to prove that Cl or Br in the molecule. So the blue line, again, these are the spectra of the ester and the ketone. We're going to think of the blue line as methane, where for every carbon signal you see, you're then substituting an H for whatever's bonded to that carbon. So we already said, based on the shift difference, that blue one was this signal here. So starting from 0, the first signal we see is at 39.1. So how do I want to phrase this? I want to color that green and then that yellow. So would the signal at 39.1 be the green or the yellow carbon? I think I heard green. So it's going to be the green one. So therefore, the last one has to be yellow. So why is that? Well, the yellow one's bonded to oxygen, right? And we know from electronegativity that it should push it further away from 0. So that's one way to explain the location of the second one. The location of the green one, again, this CH2 looks the most like methane, so it should be closer to 0. From methane, you've taken an H, you've substituted it for a CH2. You've taken an H, you've substituted it for a carbonyl. So for every substitution of an H you do, it's going to move it somewhere within that spectral width. So in the last couple minutes here, we have three sp3 carbons in the ketone we need to assign. Of those three, you can look at the grouping, right? 2 of them are close together and one's off by itself. Do you see the pattern of the 2 that are similar? And then the one off by itself. So we can differentiate that. We have 2 times CH3 and then 1 times CH2. Don't fall into the trap by thinking, well, these are both CH3, so it has to be those. And then that should be the CH2 because that could differentiate them. The way you want to think about it is, which one looks the most like methane? So it's going to be the CH3 at the end of the chain. So I'll call it the green one. So that green one is that signal there. That looks like the most like methane. The other 2 are both bonded to the carbonyl, so they should be in the same region. But one's a little bit further than the other. So this CH3 is that one because it's only been substituted once. And then with red here, that one has a carbonyl bonded to it and then a methyl group. So it shifts it a little bit past that other methyl group that's bonded to the carbonyl. So we have about a minute left. Let me check out what's... Yeah, I think we'll just wrap up there, but that's essentially what you're doing when you interpret carbon NMR. Where do the signals fall, what region, what functional group, and then you sort of use this additivity relative to methane to help you do the exact assignments. So on Monday, we'll pick up with proton NMR, which has a lot more stuff to talk about, but we're still going back to the uniqueness. Don't forget to do your quiz. That opens up. Next.